Okay, today we're back to finish our discussion about volume, density, and pressure. Yesterday we ended up discussing the vertical variation of pressure in a liquid, and we're going to summarize that again to start today. We're going to go over some applications and then a little discussion about pressure measurements, and then we will move on to hydraulics. Here again are the learning objectives. So we ended yesterday's class by discussing how the pressure changes with depth in a fluid. And so at any depth d in a fluid, the pressure is equal to the pressure at the top of the fluid plus the pressure due to the weight of the fluid above that height d. And it's given right here. P is equal to P0, where P0 is the pressure at the top of the fluid. In this case, it's the pressure, the air pressure due to the atmosphere above it. And the second term is the pressure of all the fluid piled above, the weight of the fluid piled above the point D. And so the pressure increases with depth because as you go deeper into the fluid, the weight of the fluid above you is increasing. So the question here, let's start with a couple examples here. Is this first case possible? Okay, so you have two cylinders here, and they're both exposed to the atmosphere. Can the height of the fluid in the right arm be larger than the height of the fluid in the left? And the answer is no. So why not? Okay, so both of the arms are exposed to the atmosphere, and so the pressure at this point is P0, it's the atmospheric pressure, 1 atmosphere, and the pressure at this height is also 1 atmosphere. And we also see here that the pressure at a depth d below the top of the surface, only depends on the distance d and not on the area A of the arm. And so this distance d of the fluid, the height in this arm, is higher than the height in the left arm, or in other words, d1 is greater than d2. But for that to be the case, the pressure at this point here, P1, would have to be larger than the pressure here, P2. And if that were the case, you would get a net force which would push fluid up the left arm until the two heights were equal. And so if both arms are exposed to air, the heights of the fluid in each arm cannot be different. They must be the same. And so the answer to this first one, part A, is no. Okay. So let's go over and try this experiment here in B. So is P1 greater than P2? Okay, well, to answer that question, let's look at both arms have a pressure, atmospheric pressure, the same atmospheric pressure here. And P1 and P2 also correspond to the same height below the surface of the liquid. And so, since they both start off with the same pressure, P atmosphere, and both points lie at the same distance d, the same depth of the fluid, then therefore they must be at the same pressure. And again, if they were at different pressures, you would have the side with a greater pressure, the fluid would get pushed up the other side until they became equal. Okay, and this is convenient here because if they're both the same depth below the fluid, we can draw a horizontal line, and the pressure must be the same at any point on this line inside the fluid. And so if we know the pressure on this left side, we can draw a horizontal line, and we know that the pressure must be the same on the right side. Okay? So, in summary, the pressure of the fluid inside a fluid increases proportionally with depth d in the fluid, and that's just because the weight of the fluid above it becomes greater as you go deeper into the fluid. Okay? Now, this is not the case, such a simple equation is not the case with the gas. And the reason is we made the assumption that the liquids are incompressible, which they are, and that the density is constant. Okay, you can't compress a liquid, but you can compress a gas. And here's an example of Earth's atmosphere. Density of the air density is greater near the surface of the Earth, and it's less up as you go up in altitude. And since the weight, the pressure due to the fluid is due to the weight of the fluid above it per unit area, if we go up in altitude, there's less weight above that point, and so the pressure is going to be lower. And as we go toward the surface, there's more and more weight of the air piling above us, and so the pressure will be greater. And the net result is that the pressure decreases with altitude, just like with a liquid, but not with such a simple equation as a liquid. And here's another picture. So it's always the weight of the air molecules above you at a given altitude which are giving rise to the pressure. Okay, and so again, as you go higher in altitude, there's less weight of air above you, and so the pressure will become less. And so pressure is greatest at sea level, and it's smaller as you go up in altitude. And we can derive a similar equation as we did for fluids that works pretty well for the atmosphere, and this is what's called hydrostatic equilibrium, meaning if the sum of the forces on a given chunk of air is zero, so that the upward force and the downward force are in balance and the air isn't accelerating, we can derive that the pressure follows this equation right here. The pressure at an altitude z is the pressure at sea level, and it decreases exponentially with altitude. Okay, so the sea level pressure we know is 1.01 times 10 to the 5th Pascal, or 1 atmosphere, so we plug that in for P0. This scale height is defined as the altitude at which the pressure drops to 37% of its value at sea level. And in other words, when z is equal to z scale, or whenever the height is equal to this constant z scale, then this becomes x to the negative 1, because these are equal, and e to the negative 1 is 0.37, and so the pressure at that altitude is 37% of the pressure at sea level. Now, for typical atmospheric temperatures and conditions, this scale height is about 8 kilometers, which means that 8 kilometers above the surface, the pressure has dropped to about 37% of what it is at sea level. So let's look here. I made a little plot of the pressure versus altitude. And if we look here, the pressure at sea level is about 100 kilopascals. And if you go up to about 12 kilometers, the pressure is down to about 25% of what it is at sea level. So let's look at the altitude of Boone. So Boone's about 1 kilometer up. And if we go to 1 kilometer, the pressure is about 90 kilopascals, or about a little less than 90% of what it is at sea level. And in fact, if you take a pressure sensor and you measure the absolute pressure at this altitude, it is always very close to 90 kilopascals. Okay, let's look at a few other cases. Suppose you're going out to visit your friend in Denver. Denver's the mile-high city. 1 mile's about 1.6 kilometers. And we see that if you live in Denver, the pressure's a little less than 85% of what it is at sea level. And in fact, this is why sometimes people feel a little joint pain or a little shortness of breath if you go and work out after out in Denver and you're used to working out at a lower altitude. Couple more examples. Suppose you're out in the Rockies and you go hiking. There's a lot of 14,000 feet mountains out there. 14,000 is about 6 kilometers up. You climb to the top and you are less than 50% of the pressure at sea level. And so that's why it's a little bit harder to breathe when you go up there. And if we go up to Mount Everest, which is about 29,000 feet, 8.84 kilometers, the pressure is only about 1/3 of what it is at sea level, okay? And at this point, this becomes dangerous where people black out and die. So not a smart thing to stay up there any longer than you have to. And so this illustrates why the pressure decreases with altitude. Okay. Now suppose you want to measure pressure. And you take your tire gauge out. What are you really measuring? And the answer is you're not measuring the absolute pressure with most pressure sensors or like a tire gauge, but really what you're measuring is what we call gauge pressure. And gauge pressure is equal to the pressure in excess of atmospheric pressure. So the total pressure, the absolute pressure, is the atmospheric pressure plus this extra pressure, which is called the gauge pressure. Sorry about that. And the atmospheric pressure, if you convert it to PSI, which is what gauges typically, tire gauges use, 1 atmosphere is equivalent to 14.7 pounds per square inch of pressure. Okay? And so if your tire gauge, you measure the pressure of your tire and it says 32 PSI. Well, what it's measuring is the pressure in addition to atmospheric pressure, this gauge pressure. And so a reading of 32.0 psi corresponds to an absolute pressure of 32 plus atmospheric pressure 14.7 corresponds to an absolute pressure of 46.7 psi. So that's just something to keep in mind, is that the gauge pressure that your tire gauges measure is the pressure in excess of atmospheric pressure. And we call that the gauge pressure. Okay. Now, many pressure sensors use this equation, which we derive for the pressure with the variation with the depth of the fluid. And so if P0 is atmospheric pressure, many gauges measure, or pressure sensors that work on fluids and some gases, measure the height d of the fluid, and they measure this term here, which is the excess of atmospheric pressure. So let's look at a couple examples here. The first is an open tube manometer. Okay, and what that is it's this column of liquid, and it's often mercury because mercury has a high density, and so you can get a larger change in pressure. So if you have two arms, and it almost looks here like underneath your sink, the U going to from the, let's forget it here. So this arm is exposed to the gas, which is at some pressure P gas, and then you have a liquid in here, usually mercury, and then you have the other end, which is open to the atmosphere, open to air. And so then we know that the pressure at the top of this fluid in the right arm is P atmosphere, and we know that the pressure here is whatever the gas pressure is. So to derive the equation, we notice that since points P1 and points P2 are at the same depth, that the pressures P1 and P2 must be equal. Okay, so we draw the horizontal line. Pressure must be the same at both of these 2 points. Okay? And we know that P1 is the gas pressure, and we know that P2 is equal to atmospheric pressure plus the additional pressure due to this height h of the fluid column, which is the density times gravity times h. And if we set these two to be equal, we get that the gas pressure is equal to 1 atmosphere plus this additional term, rho gh. Okay. And by measuring the height, h, of the fluid column, and we know the density of the fluid, we can get the pressure of the gas. And so this height gives you this excess pressure in addition to 1 atmosphere. And so that's a manometer, and that's used to measure the pressure of gas. Okay. Another example is a mercury barometer, and that's a device that's used to measure atmospheric pressure. Okay. So in this case, what you do is you fill this arm with a fluid, mercury, in this case mercury, and then you quickly tip it. And what that does is that all the fluid falls down here. There's no air above here to take its place, and so you create a vacuum up at the top of the fluid. And the pressure here then, P0, is 0, and then the pressure down at the bottom here is equal to the height of this column of fluid multiplied by the density times gravity. Now we know that since this is at the same height as this open end, that this must be at atmospheric pressure, and so these two pressures must be equal. The pressure in the open end, the pressure in the closed end at the same altitude must be equal. And we can again apply equation 3 since they're both equal. So P atmosphere, which is the pressure in the open end, must be equal to the pressure of vacuum, which is 0, plus this additional term due to the column of mercury, which is the density of mercury times G times H. And so in this case, if we measure the height of the column of mercury, that gives us That gives us the atmospheric pressure from this equation. So let's do an example here. So if we plug in the density of mercury is 13.6 times 10 to the 3 kilograms. That should be a meters square. My bad. And if we know the pressure of the atmosphere, so the question is, to what height will the mercury fluid be raised if the open end of the fluid is exposed to air at atmospheric pressure? Okay. So we apply this equation. We plug in the pressure of the atmosphere, we plug in the density of mercury, we plug in G, and we solve for the height, and we find that at atmospheric pressure, this column of mercury, the air pressure pushing down, will push the column of air of mercury up to a height of about 760 millimeters, or 29.92 inches of mercury. And that's why sometimes you'll see on the Weather Channel and on other weather forecasts, they will give the pressure in terms of inches of mercury or millimeters of mercury, because that is the reading on this mercury barometer. So atmospheric pressure pushes down on the fluid, and it raises the height of mercury in this column to about 29.92 inches. Now, as the second part of the problem, suppose that there's a high pressure system and that the pressure raises just a little bit from 13.6 millibars, 13.13, or 10.13 to 10.16, so just a small change in pressure. Okay. By how much is this going to raise the height of the fluid? And the answer is that it will raise the height of the fluid. If we calculate here, it'll raise the fluid about 2 millimeters from 760 millimeters to 762 millimeters. And so it doesn't raise the height of the fluid much with small changes in pressure. So these are two instruments which measure which apply this equation for the variation of depth of pressure with fluid depth to measure either the pressure of a gas or to measure atmospheric pressure. So that pretty much concludes these lecture notes, where we've discussed pressure and we've discussed density and we've discussed mass. So let's move on to the next set of notes. So here we go. Slideshow, concurrent slide. And we are going to cover Pascal's principle and Archimedes' principle. And so these are two more important applications of fluid dynamics. The first one, Pascal's principle, governs the behavior of hydraulic systems, lifts, brakes. And the second, Archimedes' principle, is related to buoyancy and why we tend to feel lighter when we're in water or a fluid than when we're not. So again, your first assignment is due Wednesday the 27th. And this is going to cover sections 14.3 to 14.4 of the chapter. Here's your learning objectives. You can look at these when you're done, what you should be able to do. So we're still dealing with fluids that are at rest. In other words, the fluids are not moving. This is what's called hydrostatics. Hydro is fluid, static is at rest. And so we'll move on to fluids in motion after this. So quick review. Again, I hate to beat this to death, but this equation is very important with liquids, is that the pressure at some depth d in the fluid only depends on what the pressure is at the top of the fluid, and then this additional term, which is due to the weight of the fluid above a given point. And since it only depends on the distance, the depth d in the fluid, we can draw horizontal lines, and the pressure at any point along this line in the fluid has to be the same. So we've made the claim that this second term is due to the weight of the liquid above a given point d at given depth of the fluid. And basically that's because the density times the volume, which is density times the area times d, is equal to the weight of the fluid, and the weight of the fluid, or is equal to the mass, and the mass times g is the weight of the fluid. So this second term is just due to the weight of the fluid. So let's look at Pascal's principle. What does that say? Well, if you have 2 points, what it says is that if we apply an extra bit of pressure at the top of the fluid due to maybe applying a force, or maybe due to pushing on your brake pedal, the master cylinder of the braking system, that creates an additional pressure, which is equal to the force divided by the area. And that additional pressure must be applied equally to all points in the fluid. So in other words, if I increase the pressure of this fluid at this top point by 2 pascals, then an additional 2 pascals of pressure is applied to all points in the fluid. And it's pretty simple by looking at this equation. What we're doing is we're just changing the pressure P0 at the top by adding a little bit of force to it. And then the pressure at any point will be increased by the same amount. Okay. And so one example here is a hydraulic lift. And we'll get into this more in a minute. But if we apply a force F1 here, what that does is that creates an additional pressure, which is the force per area, which is force F1 over A1. Well, that will apply the same increase in pressure right here. And so the added pressure must be the same here in this cylinder as it is in this cylinder. And since pressure is force per area, therefore the force is pressure times area, a small change in pressure applied over a large area can give rise to a large force, F2, which can be used to lift a car or to lift something that is heavy. So we only need a small force here, F1, to produce a much larger force here, F2. In other words, the force gets amplified. So here's the same thing. It's easier to visualize if we take 2 points with the same height. I mean, this applies even if they don't start off at the same height, but there's a little bit more math, so let's just keep them at the same height. Okay? So since P1 must equal P2, since they're the same height, then we have F2 is equal to P2 over A2, F1 is P1 over A1, and since P2 is equal to P1, they cancel, and what that says is that F2 is equal to F1 multiplied by this gain in the force, which is the ratio of areas. And so this is the amount by which the force is amplified. And so if we have a larger piston, a larger area over here on the right side than we do on the left, we only have to apply a small force to get a much larger force. And if any of you most of you have used a car jack before, we see that, right? We only need to apply a small force to the handle to lift the car up. So here's the same thing again, arising from Pascal's principle. So this isn't magic, okay? So you apply a smaller force here, and that produces a larger force over here. But conservation of energy says that you can't get more work out of the system than you put into the system. So if we displace this piston by an amount d1, the work that we do is the force we apply, F1 times d1. That cannot be any greater than the work F2 times the displacement d2 of this piston. Okay? And since F2 is much greater than F1, you must have d1 must be greater than d2. And so, other words, we must displace this volume of fluid over a much greater distance, d1, than we get back in how much this arm is raised, d2. And so we apply a smaller force over a larger area, and the return from this is that we get a larger force but a smaller lift. It only is applied over a smaller area. And this just comes out of conservation of energy. So here's an example. So the lift of the cylinder, you have a hydraulic lift, and the left side, the lift cylinder, the right side, I mean, has a diameter of 25 centimeters, and the left one has a diameter of 1.25 cylinders. So calculate the force multiplication factor, F2 over F1, and then use that to get the input force that is required to lift a 2,000 pound car, where 2.2 pounds we showed last time is 9.8 newtons, or 1 pound is 4.448 newtons. And after you do that, then calculate the distance d1 that the fluid must be moved in order to lift the car by 30 centimeters, which is 1 foot. Okay, so stop your video here, work out the problem, and then come back and look at the answer. So, okay, hopefully you worked out the problem. Okay, so the ratio of the output force that's exerted on the vehicle to lift it divided by the input force, which in reality is supplied by a compressor. For a hydraulic lift system, it pushes compressed air to increase the pressure of the fluid. The ratio of the forces is just the ratio of the areas, A2 over A1. And the area of a circle is just pi r squared, where r is half the diameter. And so the pi's cancel, the 2's cancel, and the ratio of the forces is just the ratio of the square of the diameters of the two cylinders. And that's equal to 25 over 1.25. And so the ratio of the diameters is 20, which means the ratio of the forces is 400, which means you get an output force that's 400 times greater than the input force. Okay? So now what we want to do is we want to lift a car that weighs 2,000 pounds. And so we need to apply a force which is 1/400th of its weight, which is 5 pounds or 22 newtons. And so we only need to apply 5 pounds of force to hoist a 2,000 pound car. So the catch is that that distance over which the fluid must be displaced by this force F1 must be at least 400 times greater than the height at which the car is raised. And so if we want to raise the car by 30 centimeters or 1 foot, we need to apply our force over 400 feet or 120 meters. And that work is done by pumping oil into the small cylinder using a compressor. And so the main point here is that with any hydraulic system, we only need to apply a small force at the input to get a large force at the output, where the amplification of the force is the ratio of the areas. But we need to displace the fluid over a much larger distance. Okay? So it's kind of like walking home and you have to go up a large elevation gradient. We can either go up a steep slope and walk a smaller distance, or we can spread the pain out and go up a smaller slope over a greater distance. Okay, it's the same thing here. We're trading off force for displacement. So I have a YouTube video here on hydraulic braking systems, so let's put that on. It's pretty good. Where is it? Here it is.
Pascal's law. Pascal's law was formulated by Blaise Pascal to describe the effects of pressure within a liquid. The law states that the pressure exerted anywhere in a mass of confined liquid is transmitted undiminished in all directions throughout the liquid. The working of hydraulic devices like the hydraulic press and the hydraulic brakes are based on this principle. Hydraulic brake system. We all know that a car slows down and stops when we apply brakes. But how does this happen? How does the force exerted on the foot pedal stop or slow down a car? How does it multiply the force so that it is enough to stop something as big as a car? The basic idea behind any hydraulic system is very simple. The force applied at one point is transmitted to another point using an incompressible fluid, generally oil. Most brake systems also multiply the force in the process. Here you can see the simplest possible hydraulic system. Two pistons are fitted into two glass cylinders filled with oil and connected to one another with an oil-filled pipe. If you apply a downward force on one of the pistons, then the force is transmitted to the second piston through the oil in the pipe. Since oil is incompressible, the efficiency is very good. Thus, most of the applied force appears at the second piston. The advantage of hydraulic systems is that the pipe connecting the two cylinders can be of any length and shape, allowing it to choose any path separating the two pistons. The other advantage about a hydraulic system is that it multiplies the force applied. Here you can see the hydraulic brake system of an automobile. It consists of a pipeline containing fluid, one end of which is connected to the master cylinder, fitted with a piston attached to the foot pedal. The other end of the pipeline is connected to the wheel cylinder, having two pistons, P1 and P2, attached to the brake shoes. The area of cross-section of the wheel cylinder is greater than the area of the cross-section of the master cylinder. Let us see what happens when brakes are applied. When the brakes are applied, the foot pedal is pushed, due to which pressure is exerted on the fluid in the master cylinder. This pressure is transmitted equally and undiminished throughout the fluid and to the pistons of the wheel cylinder. Therefore, the pistons get pushed outwards and the brake shoes get pressed against the rim of the wheel, due to which the motion retards. On releasing the pressure on the pedal, the return spring forces the pistons of the wheel cylinder back, and the fluid flows back into the master cylinder.